All right, today we are doing notes number 27, and we're talking about right triangle trig. You might remember this, some of this from geometry. You learned SOHCAHTOA, I believe, to solve right triangles and figure out missing sides and angles. So we're going to be doing a little bit of that today. We can represent trig functions in a lot of different ways. So we're looking at the perspective of right triangles for this. So like I said, remember SOHCAHTOA. And if you don't remember that, I'm going to explain what that is. But this was like the quick little way to remember what the relationship is between sine, cosine, and tangent and the sides of a triangle. So using the lengths of the three sides of a right triangle, you can form 6 ratios, more than just sine, cosine, and tangent, to define the 6 trig functions when we're looking at some acute angle theta. One note I want to say is always write the theta. So sine theta, cosine theta. You have to have an angle or a symbol for an angle there. You can't just write sin, cos, tan, whatever. That doesn't mean anything. So you have to have, just like we would write f of x instead of just f. All right, so the 6 trig functions are listed below. So suppose we have a theta somewhere in the triangle, so it's defined to be here. That means that this leg is the opposite leg, and this leg is adjacent, which means next to. And then the hypotenuse is always the longest side of the triangle, and it's across from the right angle. So the sine theta function is defined as the opposite side over the hypotenuse. So that's where we get so from, to help us remember that. Cosine theta, that function is defined to be the ratio between the adjacent side and the hypotenuse. So that's our ca. And the tangent of theta is the opposite side over the adjacent side, and that's where our TOA is. Now, there are 3 other trig functions. These are just the reciprocals of the first 3. So CSC is for cosecant. That's the reciprocal of sine. So the cos do not go together. So sine and cosecant go together. That means this is hypotenuse over opposite. I don't have a thing, like I don't use the letters for these. I just know what they're reciprocals of. I guess this would be CHO. Secant would be hypotenuse over adjacent. And cotangent would be adjacent over opposite. So all I'm doing is taking the 3 that I know and creating a reciprocal. Use the triangle to find the exact values of the 6 trig functions of theta. So exact values means no calculator. We will leave things in radical form and go from there. So in order to solve a right triangle, you need to know what the 3 what the 3 sides are. Remember, we do have Pythagorean theorem where a squared plus b squared equals c squared. You also have Pythagorean triples that you may or may not remember. So for example, 3, 4, if you have side lengths of 3, 4, a lot of you might know the hypotenuse is 5, but you could also do the math on that. 3 squared plus 4 squared equals whatever this missing side squared is, and that comes out to 25. And since we can't have a negative side length, we do get 5 for that. All right, so I need to write out the 6 trig functions. Again, I have to write sine theta. So theta is right here. So 4 is the opposite, 3 is the adjacent, 5 is the hypotenuse. So sine is 4 over 5, opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, 3 over 5. If I needed to, I would reduce these fractions. Tangent theta is 4 over 3. Once you have those 3 defined, you just need to flip them to get the reciprocal functions. So the reciprocal of sine is cosecant theta. That would be 5/4. The reciprocal of cosine is secant theta. That's 5/3. The reciprocal of tangent is cotangent theta, and that's 3/4. So those are my exact values of my 6 trig functions of theta. Now, for the next one, I can do the same thing. I'm going to show you 2 ways to do this. I do want to make a note. The best way to do this one is to reduce the triangle, and I'll explain why we can do that in a minute. I'll show it without reducing first. If I don't reduce the triangle first, let's say this is our missing side. So I need to do Pythagorean theorem because this is not a triple that I know. So it would be x squared plus 2 squared equals 4 squared. Excuse me. So x squared equals 16 minus 4, so 12. So x equals 2 radical 3 if I square root. All right, so we know this is 2 radical 3. Now, every time I do trig functions, notice that these three sides all have a common factor of 2. So every time I go to write out one of the three trig functions, I'll start with sine theta. I'm going to have something I need to reduce. Opposite over hypotenuse gives me 2/4, but I always have to answer in lowest terms for the AP exam, so the answer is actually 1/2. Cosine theta would be 2 radical 3 over 4. But again, you have to reduce 2/4. So that's really 1/2 radical 3 or radical 3 over 2. And tangent theta is going to be opposite over adjacent, 2 over 2 radical 3. Those 2's can cancel out. We also have to rationalize our denominator. So multiply by radical 3 over radical 3. This becomes radical 3 over 3. Now, I could get around working with larger numbers and reducing, especially if these numbers get bigger. Let's say this is 20 and 40. I don't want to have to do like 40 squared minus 20 squared, figure out what the missing side is. You can reduce the triangle. So what you can actually do is create a similar triangle. So what you're really doing is saying, there's this similar triangle that has the same angle theta, but I'm going to cut all the sides in half. I can divide by 2 in this case because that's the common factor. So here's my smaller triangle. The hypotenuse is only 2. The opposite leg is only 1. And then I have smaller math to do to figure out this third side. So x squared plus 1 squared equals 2 squared. 4 minus 1 is 3. So x equals radical 3. So see how if I use the smaller triangle, then I get right to sine theta equals 1/2. Cosine theta equals radical 3 over 2. Tangent theta equals 1 over radical 3, which I still have to rationalize. So I suggest if you notice that the two sides you're given, it doesn't matter which two sides you're given, if the two sides you're given have a common factor you can divide by something, then you should do that to start. It makes the problem a lot easier and you're working with smaller numbers. All right, let's find the reciprocals. So cosecant excuse me, is the reciprocal of sine. So the reciprocal of 1/2 is 2. Secant is the reciprocal of cosine. That's going to be 2 over radical 3. But you have to rationalize. So you multiply by radical 3 over radical 3. You get 2 radical 3 over 3. Again, this is a rule for our AP exam, for the pre-calc AP exam. And cotangent theta, you could flip 3 over radical 3. And then you have to rationalize that. I'm doing this down here because this is not the first way you should do it. And then you should have something you reduce. But go back here. What about this one? If I take my unrationalized version of tangent and I do the reciprocal of that, I get right to the answer right away. So try to keep that in mind. If you rationalized an answer, instead of taking the reciprocal of that, go back to what you had before you rationalized. All right, in the previous problems, I gave you the triangle. You just had to find the 6 trig functions. Now, I'm giving you one of the 6 trig functions, and you have to draw the triangle, and then find the 5 remaining trig functions. I don't know what happened to my instructions there, but find the other 5. I think they're correct. I think you have the instructions on your page. Okay, so sine theta is 5/13. Now, it doesn't matter what your right triangle actually looks like. I don't ever worry about really drawing it to scale. It doesn't matter where you put your theta. I'm just going to change things up and put theta here. But you can always put theta in the same spot if you want, whatever. Wherever you put your theta, the 5 is supposed to be opposite, and the 13 is supposed to be the hypotenuse because this is the sine function. So opposite leg for theta is 5. Hypotenuse is 13. And then our missing side, we can either use Pythagorean triples, for which this would be 12, or we could say 5 squared plus x squared equals 13 squared. You have to do a little bit of math here. 169 minus 25 equals 144, and then you get your 12 that way. Once you get the whole triangle here, you just need to find the rest of these. So I have sine. Let's go ahead and do cosecant. 13 over 5. And then after sine, I'm going to do cosine theta. So cosine is adjacent over hypotenuse, 12 over 13. Cotangent, oops, sorry, not cotangent, tangent. Theta is opposite over adjacent, 5 over 12. The reciprocal of cosine is secant theta, 13 over 12. The reciprocal of tangent is cotangent theta, 12 over 5. All right, excuse me, number 4. With tangent, we're given the opposite and adjacent sides. And again, we can draw our triangle however we want. I'm going to put theta down here this time. So the opposite leg from theta is 7. The adjacent leg is 2. This is not a triple that I know, so I need to do the math over here. So, sorry, let me do Pythagorean theorem. So 2 squared plus 7 squared would equal my missing side x squared. 4 plus 49. We're coming off a break here, so I have to write things down. Okay, so 4 plus 49 is 53. That is not a perfect square. And let's see, does it rationalize? It doesn't go into, 4 doesn't go into it because it's not even. 9 does not divide into it because 5 plus 3 is 8. That's not divisible by 9. So no, I think it's just radical 53. I think it might be a prime number. All right, so there's the hypotenuse. So we have tangent. Let's go ahead and write cotangent theta. It's just the reciprocal, 2/7. Even if you mess up the rest of the triangle somehow, you at least should get 1 point for the reciprocal answer. Okay, and then let's go through. Sine theta is opposite over hypotenuse. And that's rationalized 7 radical 53 over 53. I like writing the unrationalized version first because remember, when we go to flip this for cosecant, instead of doing 53 over 7 radical 53 and having to rationalize that, just go back to this one and say, take the reciprocal of 7 over radical 53 and you get radical 53 over 7. And then cosine theta is 2 over radical 53. So similar story here. We get 2 radical 53 over 53. But when I go to take the reciprocal of that to get secant theta, that's just going to be radical 53 over 2. It's a lot of writing. I know it gets a little tedious. And on a test or a quiz, I do have the cosine theta, tangent theta, whatever, already typed out for you. But it's just a good thing to get in the practice of writing that theta every time. Okay, special right triangles. This is also something that you learned back in geometry. They're really incredibly super important to memorize these drawings because in the next day or so, we're going to be learning unit circle trig, and all of the non-calculator trig that we do this quarter basically is going to involve these special right triangles. So you have to know. Everything is based off of these. You have to memorize these. So let's start with the one that's not isosceles, so this one. So in geometry, hopefully you learned about a 30-degree, 60-degree, 90-degree special right triangle. And why are these so special? Because when you have these angles, the trig functions that we use for our non-calculator values, they're all based on these special right triangles. So that's part of why it's important, but we need to just know these numbers. Now, you might have learned in geometry with like x's and stuff, but we always reduce everything. So instead of putting an x across from 30, the shortest leg is across from 30. Let's just make that a length of 1. Whatever the leg is across from 30, the leg across from 60 is that short leg times radical 3. So 1 radical 3 is just radical 3. The hypotenuse is always double the short leg. Well, 2 times 1 is 2. So again, you had to do more with this in geometry. You had to do x radical 3, 2x, and then you had all kinds of other stuff to do. We're keeping this in its smallest whole number for the short leg, whole number form. Okay, I also need to know what is the radian version of this, because I know that we're starting off in degrees, because you're a bit more familiar with degrees, and a lot of you are in physics, you deal with degrees. But for our AP pre-calculus test, we only work with radians. So remember, what was 30 degrees converted into radians? To convert to radians, you do times pi over 180. 30 over 80, you can reduce by 10. 3 over 18 is 1/6. So pi over 6 was 30 degrees. The quick way I remember that is like 30 degrees has a 3 in it, but it's pi over 6. 60 degrees is pi over 3. Again, you could convert that, but you can just kind of say like, oh yeah, it's the opposite number. I don't know if that's helpful or not, but 60 over 80 reduces to 1/3. Looks like my OneNote crashed on me for a second there. Not a good sign. Okay, so that was pi over 3. All right, so, there we go. All right, what's the other special right triangle? So this one is isosceles. It has the same two legs, same length. That means that both of these would be 45-degree angles, 45, 45, 90, because we know that the three angles inside a triangle add up to 180. And 45 degrees times pi over 180 converted into radians is pi over 4. You can reduce by 5 if you want, and then reduce by 9, but it comes out to pi over 4. So if you see pi over 4, you're really in the 45-degree triangle. And what are the two side lengths? So again, let's give the legs a length of 1. And since they're the same, they're both going to be 1. And if you do Pythagorean theorem for the first, for the hypotenuse, it'd be 1 squared plus 1 squared is 2. And the hypotenuse is the square root of 2. In general, the hypotenuse is whatever the leg is times radical 2. All right, use these two triangles to find the exact values of each trig expression. So remember, we have SOHCAHTOA working for us, and then whatever angle they put in is what you should be using as your theta, and that dictates where the opposite versus the adjacent leg is. So let's take a look at tangent of 30. So tangent of 30 degrees. So here's 30 degrees. Opposite is 1. Adjacent is radical 3. So we're using opposite over adjacent. And then we need to rationalize that. So it's radical 3 over 3. That's the exact value, no calculator, for tangent of 30 degrees. Sine of pi over 4. It does not matter which pi over 4 angle you look at because they both have the same opposite and adjacent. Sine is opposite over hypotenuse. Excuse me. So the opposite of pi over 4 is 1, and the hypotenuse in that triangle is radical 2. And then we always simplify to radical 2 over 2. Cosine of 60 degrees. So find 60 degrees. Here it is. Cosine is adjacent over hypotenuse. So what's adjacent to 60 degrees? 1. And what's the hypotenuse? 2. 1/2. Nothing to simplify, nothing to rationalize. Okay, what about cotangent? So in my brain, I'm thinking, all right, tangent is opposite over adjacent. So this is adjacent over opposite. Find pi over 6. Pi over 6 is 30 degrees. What's adjacent to pi over 6? Radical 3. And what's opposite of pi over 6? 1. And radical 3 over 1 is just radical 3. You do need to simplify that. All right, secant of pi over 3. So secant is the reciprocal of cosine. So hypotenuse over adjacent. All right, so here's pi over 3. Hypotenuse is 2. Adjacent is 1. 2 over 1 is 2. Cosecant of 45 degrees. So cosecant is hypotenuse over, it's the reciprocal of sine. So hypotenuse over opposite. Find 45 degrees. It doesn't matter which one. The hypotenuse is radical 2. The opposite leg is 1. Radical 2 over 1 is radical 2. So these problems, hopefully, you're seeing the pattern. The problem itself is pretty easy as long as you have your SOHCAHTOA straight. The biggest part is it's easy because we have the triangles drawn. So the triangle will not be provided for you. Your job is to memorize how to draw these two triangles so that you can then use them for reference. Eventually, we will work with these so often that you kind of have things memorized, and I'll show you a shortcut for how to do these without triangles, but we'll get to that in a week or so. Cosine of pi over 3. So here's pi over 3. Cosine is adjacent over hypotenuse, and so that's 1 over 2. Tangent of pi over 4. Tangent is opposite over adjacent. 1 over 1 is 1. When we have speed quizzes, they will be these problems. What's the tangent of 30? What's the sine of pi over 4? What's the cosine of 60? You could draw right triangles, but I will also show you another way because we will expand beyond just the 30, 60, 90, 45 angles into angles between 0 and 360. So we'll talk about that more. Okay, what about applications? The applications, you'll use a calculator. We're going to use Desmos this year, which is why I re-recorded this video. So in general, for application problems, if you're not given a picture, you should draw a picture, label what you know, label angles, maybe put variables for missing parts. Based on which sides are given, so do you have opposite hypotenuse or opposite adjacent, whatever, pick the corresponding trig function and set up an equation. Most often it's a tangent function. It's usually known, like usually we can measure easily a horizontal distance and a vertical, and we're usually looking for a hypotenuse or an angle or something. Solve your equation, make sure you label your answer, and round, always round to 3 decimal places. All right, so a surveyor is standing 50 feet from the base of a large tree. So here's our surveyor, here's our tree. This distance is 50 feet. Let's assume the tree is perpendicular. The surveyor measures the angle of elevation, the angle of elevation to the top of the tree as 71.5 degrees. How tall is the tree? How tall is the tree is the unknown. So here's the tree, X. It doesn't say anything about a person being up here, but I did this kind of as the notes as well. An angle of elevation is always from the ground. If you had, say you had like a something that opens up, it's flat on the ground, and then you open it up until it's pointing at the tree. So this is an angle of elevation. And I wasn't given one in this problem, but there's this opposite interior angle. You might remember that from geometry. If I draw like a parallel line to the ground and I put this transversal in between, I get these two angles, which are the same angle. This is called an angle of depression. So imagine I had in this problem, I had someone standing in the treehouse and they're looking down at this person on the ground. Their angle of depression would be 71.5 degrees as well. So angle of depression, anytime I'm given that, it's also, I just draw it as an angle of elevation to get it inside of the triangle. So that's 71.5 degrees, that thing. And so is that actually. And we want to know how tall the tree is. So the height of the tree is the leg opposite, 71.5, and the 50 feet is adjacent. So which trig function uses opposite and adjacent? That's tangent. So it would be like this. It's always tangent of the angle, but instead of theta, I know the angle is 71.5 degrees, equals opposite over adjacent. How do I solve this for x? Well, it's x divided by 50 right now, so I'm going to multiply the 50 over here. And I need to check the mode of Desmos before I just go typing this in. On our AP test, Desmos will be in radian mode because we will only have radians. But when I just open it in the website, I can't remember what form it's in. And I feel like sometimes it changes in our test mode app. So click this little wrench and see what it's in. So right now mine's in radians, but I have an angle in degrees. So I'm going to switch this to degrees. And then I'm just going to type in on my home screen here, 50 tangent 71.5. And it gives me a tree height of, oh, that's a tall tree, 149.434. And that would be labeled in feet because that was the measurement of the one side length that we had. All right. At a distance 19 feet from its base, the angle of depression from the top of the flagpole to a point on the ground 19 feet away is 64.6 degrees. How tall is the flagpole? Okay, so for all of these, you have some sort of right triangle, right? So if you don't know where to start, try just drawing a right triangle. How tall is the flagpole? So that's our X again. So here's our flagpole right here. Angle of depression. So the angle of depression from the top of the flagpole to a point 19 feet away, so down to this point, which I now know is 19 feet away, is 64.6. So that's not this angle right here. That's this angle out here. And remember, anytime we have an angle of depression, we could really say that's the same as an angle of elevation, which would correspond to this corner down here. If you were on the ground looking up at the flagpole, you would be looking at the same angle as if you were at the flagpole looking down to that point on the ground. Once again, we have an opposite and an adjacent compared to this angle of elevation here. So it's going to be the tangent of 64.6 degrees equals x over 19. I'm going to multiply the 19 over here. And then I'm going to plug this in. Oop. So 19 times the tangent of 64.6 is 40 point, this would round to 0.14. And again, I'm labeling that in feet because that's what the other dimension was given in. We can also solve for missing angles. So if I want to solve for the angle, how do we get rid of a trig function and solve for x? So there are such things as inverse trig functions, and we will have a whole section dedicated to inverse trig functions. But for now, we can just go ahead and use them. So what I mean by that is, and we're going to solve in both degrees and radians. So what I mean by this is if I want to get rid of this cosine x, what I can do is say I'm going to take the inverse cosine, which would look like this, just like inverse function notation. Let's take the inverse cosine of both sides. Inverse cosine cancels with cosine. X equals whatever inverse cosine of 3/5 is. Well, let's see what that comes out to. In your Desmos calculator, whatever mode you're in is what your answer label would be. So I'm in degree mode. I'm going to type in cosine. It's kind of like I'm doing an exponent to the -1, but, well, I think, let's see. Let's see if this works. So it's not reading this. Cosine inverse is not the same as 1 over cosine. Yeah, this is right. I'm getting 53.130 degrees. So when you type that in, let's make a note of that actually. Let me write this number down first. 53.130 degrees. If I want the answer in radians, which I do, the direction said to do that, I can just switch. See how it just switched? Degrees, radians, degrees, radians. So radians, it'd be 0.927. And we don't have a label for radians, so I like to just write the word radians if I'm looking at both here. But I do want to make a note here. Cosine inverse is not 1 over cosine. It's not an exponent. It means inverse cosine, not exponent, not cosine to the -1. Even though that's how we type it, that's not what it means. All right, so here's one more problem. You are 200 yards from the river. Rather than walking directly to the river, you walk along a straight path to the river's edge. Find the acute angle theta measured in degrees and radians between this path and the river's edge. So there's a picture for us. We have a theta right here. We have an opposite leg, and the 400 is the hypotenuse. I know that because it's across from the 90-degree angle there. So if I have the trig function with opposite and hypotenuse, that's sine. So sine of the angle, which is unknown, it's theta, equals opposite over hypotenuse. I can reduce that or not. I'm going to use a calculator. So sine of theta equals 1/2. So what do we do to find theta? We take the inverse sine. Theta equals the inverse sine of 1/2. What you're technically doing is taking the inverse sine of both sides. I don't normally show that, but sometimes it's kind of nice to know that that's what we're doing for maybe some AP questions. So sine inverse of 1/2. Oops. Yep. Oh my gosh. Okay, there we go. This is the answer in radians because I'm in radian mode. So let me answer this. So theta equals 0.524 radians. And what is it in degrees? 30. Yeah, when we did, I think we did this in an earlier example. This is a 30, 60, 90 triangle. If you reduce the sides by 200, you get 1, 2, and the missing side would be radical 3. All right, this was a long day of notes. I think we might have split it up into 2 days in the classroom. But yeah, come see me in office hours if you have any questions.